Can you define the area?
That's my starting point. Thank you very much. So what is the area of a circular disk?
The formula?
Yes.
Pi r squared.
Great job. So this is our function. It's a function of r, and it's pi r squared. Good. Now let's identify what this is, and let's identify what this is. What is 24?
24 is the ideal target.
R, it's the radius.
Oh, yeah.
And what is 0.2?
The amount it could vary.
dr. If this is x, then this is dx, right? If this is r, then this is the error in r, the differential of r. Very good. Okay, then, so now we want to determine the maximum error calculated using differentials. So how do I determine the differential of a function? What is the notation? Differential of a of r is, anyone? How do we denote the differential of a function by?
dr over, or dx over dr, or dA over
That's it.
dr.
That's it. The differential of a is dA. Good. Now what does it equal to? The formula first. Anyone?
Two pi r.
Say it again.
2 pi r.
Formula first.
Pi r squared.
Formula for dA first.
A prime times dx.
Thank you. A prime of r times dr. Perfect. Good. We established the formula now, so now we want dA. How much is A prime of A? Of r, sorry. You already gave it to me at some point.
2 pi r.
Pi r.
Very good. dr. This is the approximation maximum error in the calculated area using differentials. And you can see what's this. We're going to have to plug it in when we'll figure it out in a moment. Okay, so now let's plug it in. So we have dA equals, I have 2, I have pi. What else do I plug in?
The 24.
Very good. And what else?
0.2.
That's it. Whatever that equals to. So 2 times 24 times 0.2 times pi. Okay, so we have 48 times 0.2 and times pi. Okay, I got 30.1593. Measurement unit. 30.1593. Measurement unit.
Centimeters squared.
Thank you very much. Great job. Part B. So you notice what I said from last time, an error in the x variable, an error in the independent variable will trigger an error in the function. What we determine with the differential is an approximate. We can also determine the exact, but we are asked to use differentials. If we want to use the exact, then we will have to determine the area with 24 and the area with 24 plus 0.2 to find the maximum area, and then subtract them. Maybe I should write this down for you. The exact will be delta A, which is A of 24.2 minus A of 24. And from here you can determine the exact and compare it to that. That is an approximation, and we don't really want to do this. But you can convince yourself that these will be very close. The error is 0.2. So the exact change in the area triggered by an error in the radius will be very close to this. Okay, part B. What is the relative error? And finally, they also want the percentage error. Okay, so let's talk about the relative error first, and then percentage is the percent of this. So if I get here as an example, let's say 0.03, then this will become 3%. That's the only difference between relative error and the percent error. And because I don't want to confuse anyone, sorry. Okay. So the relative error is the error over the exact. Okay, so what was the error? No numbers just yet. What was the error? Maximum error in the area. 2 pi r dr. What is the exact? Pi r squared. Maybe I should write error in area so it's very clear. Of course, we are talking about the relative error in area. Same thing from before, in area. Okay, of course I'll simplify. And I get twice dr over r, which is twice the error in r. And S number, I have 2. The R was 0.2 over 24. And that was that is 0.4 over 24, or 4 over 240, or 1 over 60. And I'm going to divide. It's 0.01667. And then I also have to change this into percent error, so I can answer as 1.667%. So the relative error in the area is twice the relative error in the radius. Any questions on differentials? Any questions?
Twice is by definition will always be the case, right? Only twice?
For the area, yes. For the volume will be 3 and so on and so forth. But don't draw a conclusion because you still have to look at other examples, right? We don't want to draw a... okay, and finally, last thing that I wanted to talk about here in 3.10 on page 4, linear approximation and linearization. Okay, so let's start with the linear approximation. What does the linear approximation mean? Note, any function can be approximated by a line, linear function, better, near a point. And you can say, what is all this? What do you mean? Well, I mean that I can approximate any function using a line or a linear function. How is that possible? So here it is. I have f of x, of course, our best friend, p of a f of a. Here's a f of a. Yes, of course, I'm going to draw a tangent line, as you would probably expect it already. So this is tangent at p. Can anyone give us the slope of the tangent at p? Ian, will you give us the slope of the tangent at p?
I'm not sure.
Josh?
Is it something about f of x plus a?
So
No, I'm not sure.
1.5 months of calculus didn't teach us anything. Not even how to determine the slope of the tangent line at the point on a function. What should I do? So, anyone? Sarah?
Would it be f prime of a?
So why are you keeping quiet?
Sorry.
Yes, of course, it's f prime of a, right? It's the slope of the tangent line at this point, which is f prime of a. Now I would like to determine the equation of the tangent line. How do I determine the equation of the tangent at p? I have the slope, I have the point. Can anyone shout out what do I need to do?
I use the point slope formula.
Point slope I cannot use. Yes, the point slope. I was going to say the slope-intercept form I cannot use. Yes, of course. Thank you. Thank you, Mark. Yes. Y minus y1 equals the slope times x minus x1, where the slope is f prime of a, and the point is a, comma, f of a. So then y minus f of a equals f prime of a, x minus a. And of course, you know I'm going to move this to the other side. Plus f prime of a, x minus a. You'll see this at series in the next class. So this is the equation of the tangent line, tangent to the graph of f of x at point P. This is also denoted by L of x, and this is called the linearization of f of x at a, x equals a. And this is it, f of a plus f prime of a times x minus a. Again, what does this mean? Let's go back. Very close to this point, not this, I mean very close. It doesn't matter if I use the function to evaluate or I use the tangent to evaluate the function. The difference is minor. But if I want here, then I have to redo the process and determine a new line that will approximate the function near this point. If I want here, I need to determine another line. the equation of this tangent that will approximate the function near that point instead of using the function itself. Okay, so let's see how this works. So basically, the linear approximation and the linearization are the same, but they're written differently. Slightly differently. So the linearization of L of x, so of the function is L of x, f of a plus f prime of a, x minus a at a. And the linearization is just an approximation. So I can approximate the function. So this is the linearization, and this is the linear approximation. Linear, when you see the squiggles, linear approximation. Same thing, everything the same. F of a plus f prime of a, x minus a at a. So one is the function itself, the linear equation, and the other one says the function, our function, can be approximated. Our function can be approximated by f of a plus f prime of a times x minus a, which is the same thing. So at the very top of 310, so I will then look at a couple of questions. Find the linearization. And then we can look at other problems if you want, but I think that that should be enough. So this is a polynomial. This is a trig function. This is the fourth root of x cubed and the square root. Please choose one if you can see. If not, I will choose. We can choose the trig function. So we are given f of x, and f of x is sine x. And they are giving us a pi over 6. And find the linearization L of x. Okay, so linearization L of x is f of pi over 6 plus f prime of pi over 6 times x minus pi over 6. So we're asked to determine the function that we can use to evaluate sine x close to pi over 6, to the left and to the right of pi over 6, but close to pi over 6. Okay, so all I have to do, determine f of pi over 6 and f prime of pi over 6, put it in and get the line. So f prime of x, can anyone give us f prime of x for sine x? What does it equal to?
Cosine x.
Very good. So this is cosine x. So then f prime of pi over 6. Anyone remembers cosine pi over 6? If you remember, I created a little table. If you want me to create a table again, I will. You want me? How much?
Root 3 over 2.
The square root of 3 over 2, indeed. And then f of pi over 6, which is sine of pi over 6, and that will be the nicest, the smallest one. Good, we're done. So the linearization is 1/2 plus the square root of 3 over 2, quantity x minus pi over 6. It's guaranteed that if you need to, it's easier for me to explain in degrees. So this is 30 degrees. Of course, I can inside the function, I can plug in 30 degrees, but not here. This has to be in radians, as we explained. But in what I was going to say is, if I want to approximate sine x at 29 degrees or 31 degrees, I will use the line, but make sure that those are in radians. I will use the line because it's much easier. So yes, this is not done. It has to be simplified. So let me not use two equal symbols. So 1/2 plus the square root of 3 over 2x minus pi the square root of 3 divided by 12, because I have to distribute the square root of 3. So pi the square root of 3 and 12. This is by itself, so the linearization is the square root of 3 over 2x. But then I have to find the least common denominator here, which obviously will be 12. So this is 6 minus pi the square root of 3. And this is the line, mx plus b. This is the line that approximates sine x only near pi over 6. Only near pi over 6. Any questions on this? Any questions?
I have a real quick question, Professor.
Please do.
When we're answering this, like for the exam,